Okay, I'm Jeremy from Silt, and I work in the oil and gas industry. So the tool that I use is a downhole surveying tool that transmits live data to the surface through these boxes here, and we decode that signal on surface and gives us our inclination, azimuth, gamma, pressure, and a bunch of other things. So I'll give you an introduction and then I'll go through everything specifically and give you a little more in detail of what everything does. There's just a picture of one of the rigs that I worked on. I currently work in the office right now in the research and development area, but I used to work out in the field, and either I would work in like a little trailer like that or an actual command center. So usually I work out of a command center and then have a living quarter that's on site. What's directional drilling is the client will come to us with a target in mind where we want to hit, and we drill down to that target. So we're a third-party company that comes in and is hired to hit the spot. Some of our basic well profiles, well planning, our grid systems, and our wall plots. Well profiles, just like what I was saying, there's just an overview of what the well is and where we got to go. Well planning, we give a bunch of our information that we have that we're required to give to the well planner to actually give us a map of where we need to go based on the magnetics of the earth, the dip angle, declination. I'll get into that a little bit later. But we give all that stuff to the well planner. The well planner will make the plot for us, and then as we're drilling, we can make real-time decisions on where we're going and where we need to hit. Grid systems, we utilize magnetic north, true north, and I think it's grid north is what we use. And the wall plots, I kind of already explained that a little bit. Why directional drilling is essential. One, to avoid other wells. That's probably our biggest thing, is to not hit another well. You hit another well, that's bad news. You can burn the rig down. So, crossing lease lines underground, there's boundaries, just as there is up on the surface. There's lines right in the ground, so we have to drill around these lines, and sometimes we'll go and ride that line and then come back around, and we'll go under rivers, we go under mountains, wherever we want to hit, we can go around it. The client, whatever they want, we can go around it. Same in the ocean. There's different spots that when we're drilling down, and we can go into the same well and kick off into different directions. In the same direction, it's what's called a whipstock. We can go in and project out into. Some of them will have like 25 wells in the same well when we go down in there. Hit the target wherever the client wants the target to be hit. We hit it most of the time. We don't always do that. Here's a little profile of what an average S well, as we call it. We start up on surface. Usually what will happen is that we'll drill a well in different sections. Usually what I do is they're in 3 different sections: the surface section, the intermediate section, and then the production section.
Is there a typical depth that you're going to, or does it vary a lot?
It varies a lot. Like in this situation, usually these S wells will only go to about between 4,000 to 9,000 feet. But they're drilling wells now out over in Utah, where I usually drill at. They're close to 31,000 feet now. So they'll go down and then out and lateral. And yeah, it's pretty impressive. So surface location, the kickoff point, usually we'll get to a point where we keep the well completely vertical, and then we'll get to a point where we'll kick out, depending on what we want to do and the most efficient way to do it. So then at the end of the build, we'll start to build the curve and then that's when we'll actually start to kick out, and then we'll get to a point where we get out to the tangent, and then we'll let gravity pull itself back down, and then we'll go back vertical again in this particular type of well. And that's the same as the end of the drop off or the end of the curve. And then once we get to the end of the well, that's what we call total depth. And that's when we'll come pull everything all back out, and that's when the frackers will come in.
Is there GPS involved?
No, not because, at least not in my part of it, because the GPS won't work once you're down in the ground. As far as setting up the rig and being in an exact spot, yeah, they use the GPS. And a lot of times they'll just use a regular old compass because, you know, the magnetics of where the rig is sitting, they'll just walk around and, you know, it's okay, we're gonna do it right there. A lot of the stuff is pretty basic. So just different type. I told you that we had a S well, and the other one is a vertical well where they'll just punch straight down. S wells in this area are pretty common. We don't do a lot of horizontal wells around here. Slant wells, I've only done a few of those. And then the other most popular one is the horizontal. And the same thing, they'll go down, start their build section, and start doing the curve. And then once they get to their 90-degree mark, then they'll usually will pull out and then put a different type of bit on there and motors, and we'll go in with smaller tools, as we call it, because it's easier and it's not as heavy for the rig to push all that stuff down. So then we start the horizontal part of the well. And here's some other basic profiles of what we're looking for and how we get to it. And it's pretty self-explanatory. You know, the blue being, you know, where the oil is. And a lot of times you'll see it where they'll call them stringers, especially in the horizontal type of the wells, where we'll go down and we'll try to hit those stringers, and then we'll stay inside those strings. And then we just kind of bounce up and down inside of those strings. So salt zones are pretty common for us to hit. For the EM tool, the electromagnetic tool that we use, salt is our biggest enemy. It just kills our signal. We can't propagate through the formation at all. There's another example of us hitting where we need to go and then relieving the pressure. So a lot of times we'll drill down into these pockets of gas and we'll get kicks of gas. So we have to relieve the gas. So we can maintain the gas by controlling our mud weight and actually like kind of pushing the gas back down. But sometimes we can't always do that. So we have a relief valve that comes out, and I'm sure you guys, if you live around here, have seen them burning the gas off. Even at some of the plants, they get too much gas and we have to burn it off. And sometimes when they burn that gas off, they can't control it. So they'll either shut the well in or evacuate everybody off location. And then they get specialists come in to handle it. Well planning, like I was saying before, we have to abide by the surface rules. A lot of times it's on private property, and we have to abide by the landowners. A lot of times the landowners won't have the mineral rights, and the oil companies will just go where they want to go. The leases and the boundaries, same on surface and in the ground. The boundaries are different for on surface and in the ground. Existing facilities, not exactly the production facilities. I'm not really on that side of it. Natural and man-made obstacles that we have to go around, multiple targets. Necessary to drill a directional well from an offset surface location. Not exactly sure what that is. So this is kind of an overview of our grid. So we utilize grid north and true north. Most of the time we just use true north. and same with magnetic north. We have to offset our drilling, so we have to be quite precise on where we're going to hit our targets. Some of our targets are anywhere from 5 feet to 100 feet in diameter, so we need to make sure that we're spot on where we're going to hit, so we have very little room for error. So we utilize all of these to make sure that our calculations are exact. And kind of the same thing. Depending on where we're at on Earth, we have the plus or minus for our grid and true north. This is just an overview of what our surveys look like. As we're doing our real-time drilling, usually what will happen is when we're drilling, they'll drill down either in 30-foot sections, 60-foot sections, or 90-foot sections. And then we'll stop, take a survey, and then based on those numbers, we'll do our calculations, and then we'll go back to drilling again. We'll either have to slide or we continue drilling. And I'll get into sliding here in a little bit, but just a basic overview. If you look at the very top where it says SRV, that's our number of our survey. The number on the far left is our depth that we're at, and true vertical depth. So if you look at it as true vertical depth is from the top of the well to where we're at, completely vertical. So if the well is going down like that, you know, our measured depth is going to be different from our true vertical depth. So we're this like that, if you look at it like that.
Is your zero for that always the platform, or is it the ground over the spot that you're at?
It's the platform on the rig. So we call it RKB, rig. Actually, I don't know what it means. I forgot. But usually it's an offset of about 35 feet or whatever it is. There's a lot of acronyms that.
So when you do the survey, you get to a certain point, you think where you're at, and then do you send a signal down the
Drill string?
pipe,
Yes.
and then it says, okay, here I am, and then does it broadcast?
So we can program the tool to do a bunch of different things, especially this type of tool. The sensor will recognize rotation. So as we're rotating and when we go to stop, the tool recognizes that, okay, you stopped spinning, so let's take a survey. So then we'll take a survey, do our numbers, and then depending on what we want to do, we can send a signal back down to the tool if we want to change parameters or shut the tool off or whatever we want to do. I'll get into that a little bit later, but yeah, we can send a signal down to it and it will talk back to us.
So it's basically down through the pipe? through
Yes,
the metal.
yep.
Okay.
There's a couple different ways we can do it. We can do it down through the pipe, or we can actually go through the ground itself. But inclination and azimuth, it measures a bunch of things. So if you go through over the top, actually this one's a little bit different. Oh no, the one on the bottom. So inclination, azimuth are total G's, so it'll measure all of our G's. Our magnetic field of the Earth in real time, our dip angle of the Earth, and it will do our batteries, our voltage of our batteries, pressure, internal and external pressure of the wellbore, and it will do a lot of things. Gamma too, a lot of times we utilize the gamma. When we go into our pay zones, that's where the gamma rays are the highest. So when we try to stay into those pay zones, we monitor our gamma. Not only do we monitor the gamma itself, but the geologists, when the cuttings from the bottom of the wellbore come up, the cuttings that come over, they'll go in and test the gamma rays of the material itself too. So the mud will come over the shakers and they'll go out and just scoop a little bit out and bring it back to their lab and measure it that way.
When you say gamma, is it actually the radiation, or, I mean, what's gamma?
The gamma rays?
Is it radiation, or?
Yeah, it's a type of radiation.
Familiar with that, that's interesting.
So are you getting, is there uranium mixed in with everything? Is it more radium, or what is typically?
I don't know exactly.
Okay.
Yeah.
sensors and things that you're.
Yeah, so there's type of tools that we have that are rated for high heat, and that's usually 175 C and above, 180 C and above. So yeah, it gets pretty warm. When we come out of the hole and we lay down all of our stuff, it's hot to the touch. Here's another example of our inclination angle in one of our S wells. So as we're drilling down, it takes a survey point. The most important for drilling a basic well is our inclination and our azimuth. So based on that, we can make our calculations and continue with what the client wants.
So do you use a gyroscopic type device for the inclination, or?
Yep, we use gyros too. Gyros are very expensive, so the client most of the time will not want to use the gyro unless we're having problems where we're getting close to another well. If that happens, we'll pull our tool out and put a gyro in because of the magnetic interference from the other well. So this is just another example of the TVD, or true vertical depth, and that just kind of gives you an idea of all the way down and then over. And that just kind of gives you an example of the azimuth, direction in degrees to north reference. So yeah, we're always making calculations off of north, whether it's magnetic north or true north. And so the vertical section, that's just another example of how we get to our point based off of our calculations for our vertical section. So this is a smaller example of one of our wall plots based on the depth that we're going to. And then down at the bottom is kind of our basic calculation for our inclination, azimuth, and our TD. And the VS is vertical section. And then we're always plotting based on north, south, and east and west. So we'll have a wall plot, whether it's actually, they call them wall plots because back in the day they used to put them up on the wall and actually plot them with a pencil. But we don't do that anymore, really. Kind of looks like that. So this is an actual wall plot. This is what you would see if that was put up on the wall. And some guys still use it. If the wall plot's up, I'll still go up there and plot all the spots on there. So I like to see it. The directional drillers that I work next to, my actual job out on the rig was called MWD, which is measurement while drilling. And I work next to a guy, we call them the DDs, or the directional drillers. So the real-time data that I get in and give the okay that it's good to go, I give that data off to the directional driller, and he utilizes the wall plot and actually goes and hits the spot. So between the two of us, that's our job. So what I usually utilize the wall plot for is to know each of the formations and what the propagation for my tool is. So I know, say for example, I'm going through a type of shale that the signal will probably be better. So the more wells on a pad that I get under my belt, I get to know these formations with the tool and which ones, if I need to bump the power, if I need to change the frequency, if I need to move my antennas to a different spot on location to get the best signal possible. I mean, just like in ham radio, you're kind of like you're turning your antenna.
How do they steer the head, the bit? How do they steer it?
I'll get to that.
Okay.
So on the far, I'll just give you a little overview of the plot itself. In this particular well, we're doing a horizontal, and we're going down the vertical section of it, and these are the layers that we're going through. So you can see upper gulch, and I don't know if you guys can read it, but these are all the type of formations and the depths that they're at. So this is a previous well that we have that we can make reference to. And then in this particular well, it looks like they're going to 19,128 feet. So.
And then they're going horizontal.
Yep.
So you're the navigator,
Yep, we're the navigator.
and then the other guys
Yes. So between the two of us, we make the decision what we need to do, and then he actually goes up to the floor and actually steers it. And I'll get into your question a little bit later of exactly how we do that.
What's the packet look like that you're sending back? Is there error correction in it? What are you, is it just I assume you want to do it quickly because the drill's paused.
Yes.
What data are you sending back? What format?
Yeah, so it's an encoded signal that we do utilize error correction. The signal that we use is called chirp to identify the beginning of the signal. And I'll show you a little bit more once we get into the exact of the tool itself. But yeah, it's an encoded signal that we have, and then once it gets to surface, we just decode that. Just an overview of everything that we do in this tool is based on the magnetic field of the Earth. So we have to know what the magnetic field is on location, solar storms, stuff like that. That really affects our tool. If that happens, we have to stop. I mean, it's a multi-million-dollar operation, and if we got to stop drilling, if we're going to hit another well, we have to stop. So it is what it is.
Do you go drill faster when we're at the minimum sunspot cycle?
Does it drill faster?
I mean, you said it slows up and sometimes you have to stop if there's a magnetic storm.
Yeah. We've never had to actually stop it, but we'll have to adjust our calculations based on, the storm if it's coming through. It's pretty rare. It's only happened like a couple times that I've seen, and usually when that happens, it doesn't really last that long. Not that we see in the ground. Good one, Soph. So we have to adjust for our dip angle of the Earth as well. So usually in this part of the Earth, it's 68 degrees, somewhere right around up to 70. North can be expressed in 3 different ways. Like I was saying before, true north, magnetic north, and grid north. And there's a pretty picture. These are some of our tolerances. Like what we were saying to Bob, that sometimes we do get magnetic interference. We usually have a plus or minus of nanoteslas that we can stay within parameter. And if it's not, then like I was saying before, we have to stop. And we have to see if we think we're getting close to another well, or if it's something magnetic. Sometimes we just are drilling in the Earth and we just get magnetic anomalies, and we don't know what it is. So a lot of times what we'll do, if we come into a spot that we don't know or recognize what's down there, we'll drill into it, and if the magnetics go way high, we'll make a decision whether we keep going or we stop, or if we think there's something wrong with the tool, or we'll pull back out to a spot that we can get a good mark at, and if that's still good, then we'll go back to drilling. Same with the G's. Sometimes the gravity that we measure is a little too high.
Do you monitor from the surface of, do you have instrumentation to look for like the magnetic storm and stuff, or is that just part of your basic procedure?
Well, the tool itself will measure the magnetics, but usually before the job starts or at the office will tell us if magnetics are starting to. But a lot of times it's the guys that are out in the field that actually monitor that stuff. So we'll go to a website and based on our GPS location, but most of the time it's not that big of a deal. So I'm going to get into a little bit of the assembly of the tool, of the drill string itself. I know this is pretty basic, but I'll show you some pictures here in a second. But the very bottom of it is where the drill bit is, which is down here. This is our form that we use to calculate our survey point. So like I was saying before, we have to be exact on where we take the surveys. So we're measuring from the very bottom of the bit to where our tool is. So in this case, our survey point is 51.06 feet. So we know where the survey point is taken. We have to have that by law. So we can only take so many surveys. We're supposed to take a certain amount of surveys in a certain amount of depth that we drill. In this case, we have to keep track of where the gamma is being received, so we can give the data to the client too of exactly what the gamma rays are in which part of the well. Next, we have our non-magnetic drill collar, is what we call a Monel. So because of the magnetics are so important with the tool, that the tool sits inside of a collar that is non-magnetic, and those things are very expensive. Next, we have our gap sub. So this tool right here sits inside of a gap sub. It's bolted in. So it's essentially just a dipole that sits inside there. So we bolt it in like this, and then we bolt it in like that. And then it transmits the signal out that way. And I'll show you some pictures exactly of what it is and what it looks like. So we have our gap sub. That's there in the middle with the 4 little circles. That's essentially a dipole too. And then we have a non-magnetic drill collar on the top. So here's a picture of our bits. The black knobs that you see on the bottom of the top of this bit are made out of diamond. So most of them are diamond or carbide material. So they're very expensive. So a bit like that will probably go for about $30,000 or more. The cool little things coming out of the bottom of the bit there, we call them jets, and the fluid actually comes out to help lubricate the bit itself, and to just push the mud and the cuttings out away from the bottom of the bit and push them back up the wellbore.
What's the fluid? What is it?
It's mud. Depending on, well, there's 2 types of mud. We got oil-based mud and we got water-based mud. And we do utilize air sometimes, but most of the time it's water-based mud or oil-based mud. And there's a whole bunch of chemicals that they mix in there. Depending on what we're doing in the formation that we're drilling through, we'll have what we call LCM to fill in the holes and the cracks that we're drilling through. Because a lot of times we'll be drilling and we just lose circulation. If we're not circulating the mud all the way back up to surface 24/7, we don't drill. So that's the blood of our operation. So we'll put anything from chunks of wood and walnut, all types of material that we can put down the wellbore to fill in these cracks. So, yeah. So
How many days are you working on a typical well?
the well that I was just at last was, we were going down to 4,000 feet, and that operation was probably about a week. But usually the 19,000 to 27,000 foot wells, they're like 27 days. So, yeah. And it all depends on the area that you're drilling too. Like in Texas, it's fast drilling. They'll do that depth, but they'll do it in like 2 weeks, just because of the formations they're drilling through.
What's the lifespan of one of those high dollar bids?
You can burn a bit up in a day. Yeah, yep. So most of the time, if you're doing the right drilling performance and babying the bit and actually doing what it should do, it'll last you a good week. So, and you can drill like that, but you can do it without ruining the bit. So they'll bring the bit back out, and then they'll just replace those cutters, as we call them, on the top of the bit. And that's the cheapest way to do it. Well, that's not always the case. I'll show you some pictures where they just absolutely destroy the bits. And what we call DBRs, the clients, you have to pay for that bit, $30,000 bit. So operations get real expensive real fast. So back to your question about how they steer the well. So this is what we use to actually turn the bit. We call it the mud motor. We utilize the mud to lubricate the inside of the bit as well, but also it turns the bit itself. And each mud motor has a bend in it, as you can see right here. So when you're drilling down, the motor has a bend in it, just like that. So when it's spinning around and just rotating, we're drilling the well completely, just rotating. But when we stop and we keep pumping on it, it'll turn the bit, but the motor won't turn. So when that happens, we utilize that angle and push down on it, and it'll start to turn like that. So that's what we call sliding. So we'll stop and make our calculations, and they'll say, okay, now we need to go 270 degrees, and we need to put in 30 feet to keep on track to our direction that we want to go.
And how sharp a bend can you make?
Usually it's anywhere from, the highest I've seen is 2.5 degrees. So it's not a lot, but
It takes a while to make your 90-degree turn.
yes, yep. Sometimes that build, when you make your build to hit the horizontal part of the well, it could be a good week before you can,
So,
know,
another
get out.
question. You said you have as you assemble your string, you have a non-magnetic Inconel or whatever it is that's in there, and that's to give your sensors the space they need to take their measurements. I know, I do mess around with some welding stuff, and I know occasions we've ended up with some drill stem that you just buy inexpensively, and it's not very weldable because it's magnetized.
Yeah.
Is that from the spinning of the stem, or what makes it magnetized?
A lot of times when our biggest problem is the motor itself, because of all the components that are inside of it, they're magnetic, and usually I think it picks it up from when the motor is being built. So a lot of times we'll have a demagnetizer out in the field, and then we'll run it around the outside of the motor to demagnetize it, and that won't always do the trick. But yeah, that's where our non-magnetic drill collars come in, to get away from that motor, because everything above it needs to be non-magnetic. Any questions?
And those are all rare type motors. They've been talking about how important it is to use these special materials to make these motors, small motors. And is it the same type of material that, China's got out and monopoly on?
Yeah, so the motors are made out of different materials, but as far as what, I don't know, but I do know that a lot of them are stronger than others, and they're made out of a tougher material. But that goes back to whether the client wants to pay for it or not. So if the client wants to pay, $30,000 for a motor, and when they can get one for like $15,000, that means that they can lower that price for that well. So the higher profile jobs like that, well, you'll see that'll be offshore, that kind of stuff, where they're really dumping in a lot of money.
So when you make the turns, the pipe is flexible enough to
Yeah, yep. So what we call squat too, or stretch. So depending on how much pipe that we have in the drill string, we have to compensate for each drill collar will bend so much, and it'll compress so much, and it'll stretch so much. So when we're taking our surveys and we're sliding, we have to keep that in mind of the stretching and the compressing.
And then the bit wears out, however far down, you have to do, I remember you said all the pipe and everything like that.
Yep. Yep, it's a process. Usually if you're down, 17,000 feet, it'll take, 15 hours for them to pull that all out, just to change the bit and then go all the way back in again.
Going down through a pipe, those, where you don't lose your hose.
No, so what we'll do is what they call weighting up. They'll raise the mud weight and pump that down into the hole to keep the they call it caking. They cake the inside of the walls of the well bore to keep it like that until we get all the way out, and then get back down in again, and then they'll lower the mud weight again. And that keeps the.
What's the diameter of the basic hole?
We drill anywhere from 12-inch hole to 4 inches. So usually how the wells start, they'll start real wide, and as we get down into our horizontal we're usually about, about that big around. There's a picture of our non-magnetic drill collar, Monels as we call them. Very expensive material. This is a picture of the gap sub, as I was showing you with our dipole antenna that we have here, and how it bolts in there. So you just essentially just stick it up inside there, and we just bolt it on there, and the signal is transmitted outside the gap sub.
Is that sleeve that is anti-magnetic, is that Mu metal technology?
Mu?
Mu metal, that is the metal that blocks magnetic waves?
Oh, I don't know if it blocks it, but it's just non-magnetic material. I'm not exactly sure of what the Monel is actually made out of. It's a good question. Here's a picture of our drill collars. They're all spiraled like that to help as they're rotating to, to screw in the ground. It helps, and it's really heavy too as well.
When you're drilling, does the whole casing turn?
The casing?
Yeah, there's that,
The casing comes in after the well is done.
so it's, how do they form that?
Where it's doing there.
The casing itself?
Yeah.
Well, they have yeah, the casing will just follow it in there. They have like a head that goes on the end of it, and then it just pushes it down there. And they make it up just like the drill collars. They just screw it together, and they just keep pushing it. And sometimes they can't get it to bottom. It's actually pretty common that they can't get casing all the way to the bottom. A lot of times what will happen is the well bore itself will just start to fall in on itself, and then it'll just pile up on the bottom. And there's some pictures of us on the rig. This is them on the far left, is them putting together the motor. So they have a little a sub that they put on the top. They just screw into each of them, and the drawworks will come down and pick that up, and then we just start putting it all together one piece at a time. The second picture is inside the doghouse, is where the directional driller usually works and actually makes the real-time calculations and the decisions on where to drill. So either the driller that's in the seat on the far right there is making the actual doing the actual drilling or the actual sliding, or the two guys on the left will just tell him what to do. That really depends on the client and what they want. Sometimes the directional driller is actually better at sliding and working the computer, and sometimes the driller himself will actually do it.
So this is like one of those trailers you were
Nope, this is actually up on the rig. So where the guys are standing here, directly behind them is this little housing there, the doghouse as we call it. And on the far right is one of the bits that just got absolutely destroyed. So if you're not following the right practices to conserve your bit, they'll just mash on it. So some of those rigs will, put 50,000 pounds of weight on it, on that bit, and if you are not babying it, you will destroy it. Sometimes we'll twist off, as they call it, downhole, and we'll lose our tools completely because it's just so much power that something has to give, and we lose all this stuff downhole. So we got three main tools, as I was explaining to him. We utilize the EM tool, which I told you about a little bit, that utilizes a dipole and transmits a signal through the earth. We do have another tool, it's called a mud pulse tool, that this is the bottom part of the tool. The mud pulse tool sits inside of this sleeve, so kind of like the gap sub, as I was explaining before. Instead of transmitting out of the gap sub itself, this sits inside of a UBHO, it's called, that the tool will sit down inside here. So the signal is transmitted up through the mud column itself. So when this sits inside of here, all the mud from the column goes down through here and then down through this top of this mule shoe, as it's called. And then the tool, the electronics from the tool will take this and move it up and down, and this creates your sine wave. So all that stuff, 30,000 feet, and that's all that thing is doing, is just going up and down and giving us, yep, making a little pulse. Pretty basic.
So you're really almost an analog.
It is, yep, like an analog signal. So we have a transducer that we put in the drill string, or on the mud line itself, and we just have a cable that's ran to that transducer, and we just see the difference between the voltage of that transducer, and we can decode that signal.
What will it tell you?
Will it?
If the mud's not flowing properly or,
Nope, the transducer itself will just only tell us pressure. So we do have, I'll get into that a little bit later, we do have a system where we monitor everything on the rig. So I'll get to that after this. And then we utilize our gyro. So we have, like I was telling you before, that if there's a case that we can't use mud pulse or we can't use EM, then we go to gyro. Yes, sir?
You mentioned the mud weight earlier, is that the pressure, hydraulic pressure of the fluid?
No, it's actually the weight of the mud itself. So we have the gas that is trying to push its way up, and we just make the mud heavier to push it back down. So a lot of other things come into it, viscosity and what we call low grabs, and they have a whole mud sheet that's like this long of all the stuff that they monitor, because not only like the tool is, but the mud is extremely important too. You know, it's the bloodline of the rig. So if the mud's not right, then we're not drilling. So when we would use mud pulse is in areas of, if we're in a salt zone or the EM tool won't work. So then we have to rely on mud pulse. So mud pulse is actually the first technology that they used before this came out. But it's still utilized today because you can only drill so far, and our batteries will only push out so much power, you know, before there's no more signal left.
So how long ago did you start using mud?
The mud pulse?
Yeah.
Mud pulse is probably back in the 80s, I want to say. What they did before they had the MWD tools is they used the gyro and actually sent the gyro down, and would actually take an actual picture of it on film, and then they would come all the way back out and have your little magnifying glass and look on it and to see that it was just essentially a little bubble that they were looking at. Okay, we're at 1 degree at 230 degrees azimuth. And then they would go back down, and what they would do is they would mark the actual mud motor, the bend of the mud motor, mark that all the way up the string, and then make their directional drilling that way.
Are these tools consumables or you reuse them?
We do reuse them. The batteries themselves, we do not reuse. I think they do have some rechargeable batteries. Slumberjay has a type of tool that has a generator on it, so as the mud is flowing, it will produce electricity for the tool itself. Principal operations, same thing. The dipole just transmitting its signal outside, and if you look up on the top here, this is kind of how we place our antennas. So I don't remember who asked, but this is where the rig would be itself. And we have one antenna on the BOP itself. The BOP is the blowout preventer. It's underneath of the rig, so if something happens, we can just close it off. And then usually we'll have an antenna that's out behind the command center, I don't know, anywhere from 100 yards out to or more. Sometimes the rigs nowadays have been converting over to AC power, so that's kind of our enemy, as most ham radio operators know, that our noise just gets so bad that we have to utilize different things to suppress that noise. So this just gives you a little visual of water-based mud opposed to oil-based mud. That's what the acronyms are up there, and air. So water-based mud is not as good as oil-based. So we propagate a lot better with oil-based mud opposed to water-based, just because it's with water, it's essentially a direct short to the dipole antenna. And it just gives you another idea of propagation based on the resistivity of the formation that we're going through. So that's another thing that the tool will transmit up to is once we start getting into a high resistivity zone, then we can make changes to the tool to transmit out more. So in the tool, we utilize accelerometers and magnetometers, which I'm sure most of you guys are all familiar with. As we're real-time drilling, sometimes these accelerometers, they mess up. So, and that's part of my job to recognize when those accelerometers are bad. So a lot of times it'll stick, or when it does stick, it usually has to do with shock from the tool, shock from the drill string, you know, just beating the bit up and down. The tool will only take so much before it'll just kick the can. And this is how we make all of our calculations too for our active real-time drilling. Same with the magnetometers. The magnetometers don't tend to go bad very often just because they're, you know, essentially just a coil of wire inside the electronics. Same thing, directional sensors, our X, Y, and Z's. If we didn't have that, we wouldn't be drilling. Same with the magnetometers. We'll get to a point in the well, when we're vertical in the well, we have to, our magnetometers are more, they're, what's the word I'm looking for? They're more accurate than the accelerometers. Because when you're up like this, you know, you can't utilize all of your axes as you need. And until we get out about 5 degrees or more is when we can actually get our gravity or our accelerometers, utilize those accelerometers.
The one's checking the other.
Yep. So they both are on all the time, but they're not always as accurate depending on which part of the well you're in. So we have tool faces, and you'll see later on the software that I use that the tool itself will give us real-time direction. Whether you're utilizing the magnetometers or the accelerometers, it'll tell us exactly where we're going, so the guys on the rig know where they need to slide. And our azimuth or dip angle, that once we stop rotating, that'll spit up all of that information. Temperature is another one too that we monitor. Depending on the temperature of the mud and the electronics and stuff that we use, the temperature we have to monitor that so it doesn't damage the components. So our high side of the tool, so we need to know where 0 is when we start. So based on that bend in that motor, that will always be our 0 mark. So we know once we're 15,000 feet in the ground that we need to turn 15 degrees clockwise to actually start sliding in the 90-degree direction.
Do you have like a profile of the Earth for what the temperature should be at certain depths? Is that a
No, we don't, but we do go off of previous wells. So we can go back and look on previous wells, and a lot of that information is open to the public too. So you can go to a website and to previous wells and actually get the surveys and stuff like that. So once we get our offset in our 0, we program that into the tool and make that our 0. So then we can make our real-time sliding. So this is an overview of what the tool looks like. So roughly the tool all built up. The tool sits inside of this beryllium housing, and it's usually about anywhere from 35 feet long to sometimes it's 50 feet long, depending on what components we want to build up inside of the housings. So a basic one will be, we have our gamma module, our electronics, our dipole, and our batteries. That's pretty much the most basic tool that you have. But we do nuclear resistivity. There's a whole bunch of stuff that we can build up inside the tool depending on what the client wants and needs. So on the far left, you can see a picture of what the tool looks like basically without the dipole on it. So you can see it's, you know, comes in sections and it just screws together essentially.
And mud's flowing in the outside.
Yep, yep. And it just sticks inside of that Monel. And there's a picture of my tools just laying up against the wall. And there in the middle picture, it's I'm high siding the tool to set my zero to match up with the bend of the motor.
Especially thinking where sometimes your tools will fail.
Yep, yeah, it's pretty common. They will always fail.
And when that happens, is it the same as a bit failing? Or can you put two units down and go have redundancy?
You can do that. Most of the time we don't, because the distance from the bit to where our servo point, the farther you get away from the bit, the harder it is for us to calculate and make real-time decisions on, because we have to make projections to the bit all the time. So if we're 80 feet back, that's not ideal. I mean, ideally, we'd want to know where we're at the bit at all times, but we can't do that.
So is it the same then as a bit failure?
Nope. Sometimes the bit will go and we'll keep the tool in. But if we do see that if we're drilling for a long time and the batteries need to be changed, we'll do a battery swap at that time.
The batteries, that yellow?
Yep, the batteries are these guys here. And we call them smart batteries. So these smart batteries will measure all kinds of things. It'll do shock, vibration, temperature, voltage, amperage, temperature, and
The battery itself is a sensor.
yeah. So like if I just start hitting it on the table, I can plug it in and it'll tell me the shocks and G's, and so even just it sitting right here, it's recording all of the stuff going on. So just by me picking it up, I can plug it in and it'll see that. Goes back to Graham's question. This is our software that we use. And you can see here some of the stuff that we are transmitting to surface. So we're getting our tool face offset of what's programmed into the tool of what our zero is. Our gamma counts, so we're getting 16 counts per second. And then we get it in hexadecimal as well. So not only do we get the real count itself, but we can do if we see that the measurement doesn't look correct, we can type into the computer in the hexadecimal and make corrections that way, if you will. We can send up real-time inclination. So this is, that's what it is. So real-time inclination based on the 0.98. We can plug that in and get what our inclination is in real time while we're drilling. So we don't have to stop and take a survey, because sometimes what will happen is if we're starting to do the build and we're starting to build up faster than what we want to, we'll stop the operation and then go to sliding, say if we need to slide down or slide up or left or right. So this is what we call a tool face packet. They're constantly coming up all the time, so we don't have to stop and take a survey. There's another gamma in there. Depending on what part of the well we're drilling in, we constantly want gamma because we want to see that pay zone all the time. So if we start to see that these gamma points are starting to drop off or get too high, then that means if they're going too low, that means we're going out of the formation that we want to stay in. So then we make changes to slide back in.
How often is your software updated?
Is it typically right for you?
Yeah, so this software is pretty basic. It's pretty much just calculates and it displays it. Now this one's updated probably about once a month, where it's more of a display, and you can see on here too. Let me walk around here, and as they're sliding, there's no dots up here right now, but the dots will start to come up on this compass as we have it. And as they start to turn the motor down hole, you'll see it here. And it'll go back and forth, and that's how they'll slide and see in real time.
And the yellow graph down the bottom there, that's your pulses?
Yep, these are our pulses. This is what it should look like. This is what we don't want it to look like. So we have a trailer that in our specific company, we have a trailer that we have that we can set on another well that's, you know, a mile away and transmit that data to the rig and decode it. So what you're seeing here is this is the signal on the rig with all of the noise, which is not decoding. We're just getting overrun packets. And then we have what's on our remote trailer that's being transmitted from a well that's previously drilled. And the signal looks great there. So basically on when we go to take a survey, we have our inclination, our azimuth, our temperature, our current gamma, the time, our live inclination, which is that number is from that number over here, our magnetics at that point in the ground, our dip angle to the earth, and our gravity, the G's in gravity, and how long we've been circulating. And that just gives you a display of the signal itself. And then based on how the quality of the signal itself, it'll bring us up with qualifiers, and it'll start listing them out here. And it'll tell us if our survey is good or bad. So a lot of times if we go to take a survey, some of the fluid is still moving down at the bottom of the well, and the survey won't be good. It'll mess up our accelerometers. So our azimuth will be good, but our inclination won't be.
So do you calibrate all this stuff out at the well, or do you have a cal lab back in the
Yeah,
office?
so that's what I do now in the office. I calibrate all the tools in the office. So yeah, we have to check to make sure the accelerometers and the magnetometers are all good. Questions?
So how many people are involved?
On the,
Like at the site and with the office and everything?
so on the,
What are their talents, I guess, if kids today wanted to get into
Oh,
some aspect of
to do that? Usually on the directional drilling side, there's only 4 of us. We've got 2 guys that work during the day, 2 guys that work at night. And to get into it, I mean, my degree is in electrical engineering, but most of the people that are MWDs and directional drillers, they don't have, you know, schooling. Unless you go to a big company like Schlumberger or Halliburton that will send you off for the schooling, it's word of mouth, really.
So it's on-site education.
Yeah, yeah.
Yeah, that was sort of my question is, you know, like you have to go, you talk about surveying, you know, and it's like, okay, in drones, you know, you do aerial surveying all the time, but, you know, you're not, you know, the drone pilot isn't necessarily a surveyor.
Yeah,
It's just somebody that gives data to somebody else who figures out,
yeah, yep.
what, you know, what you're actually looking at and gives you plot points and everything else to look for, you know.
Yeah.
Build your models and maps, you know.
Yeah, I mean, ideally, they want you to have the education for the job, but we're looking, the education is just a small part of what you're doing on location. You have to be able to talk to people. That's the other thing, is that you can be an electrical engineer and be super smart, but if you can't walk 10 feet over and talk to the company man about what's going on, then you can't be out there. That's the biggest problem that I've ran into, is that people just can't talk to people, or they just can't get up in the morning and go do their job. They do the job really well, but waking up in the morning is another problem.
Didn't you say once that, they'll pay, you know, the roustabouts or whoever, you know, $50 just for showing up?
Yeah,
Yeah.
yeah.
How many guys are you like you? I mean, is it, you know,
It's a very small niche, yeah. There's not many. I mean,
1,000,
oh no, there's more than that. I would probably say 10,000 maybe?
10,000 people
Yeah,
who do this?
yeah.
It's kind of how our society lasts, you know, you gotta have people that know what the hell's going on, and a lot of people don't know what's going on.
Yeah, when the time is right, I have no problem finding a job. When the oil field is booming, I got people knocking on my door.
Now, are you guys gonna be getting into, I noticed up in Aspen, they were doing a thing for heat wells.
Heat wells?
Yeah, they were putting in a bore and they were gonna monitor the temperature.
Oh, geothermal? Yeah,
And
that's
it was,
pretty.
you know, I think some of it's gonna be directional, I don't know.
Yeah, yeah, most of it is. Like right now, we're drilling a well that's lithium for lithium. We've drilled wells for helium too is another one. We drill wells to dispose of like fluid and stuff for companies. I mean, whatever they want, we'll drill a well for whatever they need.
That's fascinating. Okay.
Is there a point in time when AI becomes part of the?
It's coming very soon. Yeah, we're actually trying to utilize AI right now. That's part of what I'm doing in the office is we're trying to find a way to, because this is our receiver box and it's real susceptible to noise. So we're trying to utilize AI to essentially take pictures of the noise that is on the rig and put it into its memory so when it does come up, it all automatically filters it out. So that's what we're trying to work on right now. Good question. Yes, sir.
I don't know if it's the right time, but this technology and directional drilling and all that, I remember, you know, back when I was young and my father was in the oil industry and stuff, and the big thing at that point was dry wells. The fraction of dry wells is pretty high, and that was a major cost. Has that really gone down because of this technology?
Yeah, it has because we have so many other types of ways of looking down into the ground. Last year, I was over in Utah working, and they were doing seismic. So they had this huge deal, probably twice the size of this table, and this helicopter would come up and pick this seismic machine up, set it down on the ground, and it just started thumping, boom, boom, boom. And the helicopter would come back over and pick it back up and move it to the next spot. So based on that, they could tell down to, because I went out and talked to the guys and asked them, and they said it would penetrate like 15,000 feet in the ground. And based on that, they could tell where the formations were and all that. So yeah, it's not unheard of. It still happens. When they were down there doing the lithium, they penetrated the same well 5 different times, and they came up with nothing. So yeah, it can be very expensive.
What happens if you get water?
The water tables are usually between like 300 feet to 2,000 feet. So when we do our surface part of the well, we will drill through the water table with all natural stuff, and then we'll case it in so we don't affect the water table anymore.
Oh, activist drilling going on right now?
It's pretty slow, actually. We have a couple rigs that are out in Utah, but overall it's mediocre.
Is the peon spacing active at all?
There is 2 rigs up there that I know of.
Not active at all?
No, not like it was.
The number of permits that have been issued.
Yeah, not like back in '06.
Yesterday, that's like the latest bid the BLM put out, they had 40% of them that nobody bid on.
And is that just a function of the price of
Yeah,
$60?
it's just not the demand for it. Yeah, that's a big thing in Colorado. It's just not feasible to do it. Back to the EM tool. So we utilize a 1 hertz to a 9 hertz frequency that is being spit out from the dipole itself, which is pretty slow, as you guys know. Usually we use a 7.5 hertz. That seems to be our happy medium with the noise to speed that we need it at. And like I was saying to Graham earlier, we utilize a chirp frequency, which goes down and then comes back up, and then we utilize error correction too. But that's really slow. It's like half the speed of, regular chirp. And so in mud pulse, we utilize a 1/2 second to a 2.0 second pulse width. And that goes back to what I was saying before, how fast this guy goes up and down. So, droom, 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 droom. And that comes with all of its problems too as well. So sometimes if the pump that they're using has noise, or something's going wrong with the mud pump itself, we'll see that with the tool and we won't be able to decode our signal. So we have to troubleshoot that stuff. And this just gives you an idea of what it looks like and how the actual mud pulse is being transmitted up and how we decode it with our transducer. This is a picture of our gap sub, and we had a washout. So there's the gap itself. Oh, this is the gap itself. So at some point in time, this gap sub was welded together. And because of the pressure inside the pipe, somewhere in the drill string, something had to give. So that's what happened. A little tiny pinhole turns into a big, huge hole. And we see on surface that we lost a whole bunch of pressure. So when that happens, we got to pull out and then change our stuff out. Picture on the right is me up on the rig floor looking down at our living quarters. So those trailers is where we stay and work out of.
They have good chefs?
We don't have any man camps anymore. Not like we used to. When I used to work up in Peons Creek, you could drive down the road to the man camp, and they were amazing. Like Fridays, we would have lobster and shrimp, and yeah, we ate really well when we were out on the rig. We don't do that anymore. So this is what the new rigs look like. They're all joysticks. It's like you playing a game. So you sit in that little chair there, and you just have your joysticks, and that's how they go to drilling. And everything's all touch screen now. Both of those computer screens are touch screens, and they can do their sliding and everything all from the computer. Where back in the day, you'd actually have to go out on the floor and run the handle and actually use the machinery to turn the drill string itself to do the sliding. And on the right is another picture of the tools. You can see the dipole there, the second from the bottom, 2 batteries and electronics. So part of my job is to maintain those tools. So you take the actual electronics out, change out your O-rings, change out your batteries, make sure the dipole itself has good connections. And yeah, if anything needs to be rebuilt, you do it all out in the field. There's a picture of them making up one of the Monels, getting ready to stab the tool inside there. The picture on the right is our living quarters, so you can see it's not too bad. And there's just some other random pictures. So one on the left is one of the rigs I used to work on over in Utah. The one picture is me getting ready to program the tool. So the tool is already in the string, and then I plug into one of the programming ports on the top there. This guy right here, you can see the cable coming out. So I plug into it and program the tool to exactly what I want. And the picture on the far right is us inside the command center. Yeah. Yeah. Those are the guys.
So you have
12-hour shifts, yep. 12-hour shifts. Usually, unless we have 3 guys, and that's pretty rare. Usually it's just 12 hours. So the next system is our Pason EDR system. This is what everybody on the rig watches. These are the parameters that the rig is, drilling at, the pressures, the speed. So it's a little hard to read, but the hook load of actually how much weight is being pulled up on the drill string. This one I can't even really read. Torque, RPMs of how fast it's spinning. The flow, how many gallons per minute is being pushed through the drill string. How many hours are on the bit, circulating hours. The actual flow rate. The pressure of what's inside the string, and I think no, that's not temperature. That might be weight on bit. Oh yeah, this one's a little bit easier to read. So the percentage of mud that we're losing. So another big thing too is evaporation that comes into play, because when the mud comes back up to the surface, it goes over what we call the shakers to get the hard stuff out. We shake that stuff all out, and the mud engineers have to calculate evaporation as the water comes through the clean out system. Sometimes they'll lose like 15 barrels a day of the material, the water that's, the fluid that's being circulated through the system.
Yeah, if it's over 100 degrees Celsius coming out of the ground, it's gonna evaporate all over.
Yeah, it's pretty quick.
So do you guys write the software, or is that the company makes the?
The company that actually makes the tool writes the software. The AI software that we're working on right now, I'm writing it with another guy in the office.
You're writing it yourself?
Yeah, and like you said, we're utilizing AI to write the software too as well. So, yeah, I'm not much of a coder, but with the assistance of AI, it makes it a lot easier. I mean, I have basic knowledge of coding, but I can code like an entire software, like a basic program in less than a day. It's crazy, instead of actually typing it all out. So this system right here, and all the monitoring system that we utilize, this kind of gives you a basic overview of what's all being monitored. So it's a whole network of things that are all hooked up all at the same time, and my system is hooked up into that same network as well. So the guys that are, the company man that runs the whole show, you know, has multiple monitors up too, and we're all constantly watching all that stuff.
How much money are they spending when they start working on a project like this?
Ooh,
Or a day?
a smaller project is going to be at least a couple $1 million.
A day?
Oh, a day. Oh, I don't know. I think it's, on a smaller project, I think it's about $75,000 a day, something like that. But that number really varies.
Oh, yeah.
Here's the website I was talking about that you can see the wells. So if we think that we're going to have problems drilling and having signal issues with the EM system, I'll get on this website and look at the wells and look at the direction that they were drilled at. So then I know to go over and put my trailer on that, because we want to try to get as close as we can to the well that we're actively drilling.
So wells like that may be tapping the same pool?
Yes, they are tapping the same pool.
Yes, they are tapping
Yep.
the same pool.
Like up in, for example, up in Peons Creek, they're all tapping the same reservoir that's up there.
What's the scale on that between wells there, about how far are they?
I would say a mile. It would probably be less than a mile. Our wireless system from trailer to trailer is probably less than a mile. So we're working on a system right now where we can utilize Starlink to transmit instead of going from the trailer to the command center, we want to use Starlink to go up and then transfer the data that way down via internet. So then we can move our trailers farther than a mile away. This is a picture of my desk. You can see up on top there, I'm Payson. I actively have to watch Payson all the time to make sure that the drilling parameters are within spec and that we're not getting too hard on the tool. It's part of my job to make sure that they're not mashing on it, as we say, to get too much shock to the tool, and then it's junk. If we
Are there alarms on that?
Yes, oh yeah. So any one of the boxes that is on the screen, you can set an alarm for. So yeah, we utilize the alarms a lot. This is our logging software for our gamma. So I monitor gamma, ROP, how fast we're rotating, and when and where we're making our connections. So I need to know when they're getting ready to make a connection that we're going to take a survey. So, and you saw this software before, remote trailer and then on-site trailer software, our decoding software. I got my O-scope so I can actively see. There's like a 2-second lag to the software's O-scope, opposed to this is real time. This is the logging box for this system here. So all of our stuff is just hooked up through that and then just displayed here. This is our receiver box, which is this guy right here. That actively has filtering in it to filter out electrical noise. And then it has gains on here, a pre and a post gain, and then we have a low pass filter and a high pass filter. So depending on the frequency that we're using, we can, bring it in on each side. And then we have a downlink box, as you guys were over there were talking. That's what this big boy is. We utilize a 5 hertz signal that is being sent down the string, usually is how we do it. We have a clamp that clamps onto the BOP, and we'll send a signal down to the tool to, say, bump up the power, change the frequency. There's like 50 parameters that we can change. Questions?
At that low of frequency, you're probably fairly limited for how much data you can move at a time. So it take a while.
Yeah, so when we're at like 1.5 hertz, we'll be sitting there for like a good 5 minutes to get the survey. Just because the sine waves is getting all that data, it's really slow. We can, but that's what Graham was talking about with the error correction. We get, yeah. So when you're on the rig floor trying to slide, and it's almost like you're unzipping a zip file, we have to have our tool faces. We want to see them changing consecutively. Where if we're zipping it up and then spitting it all out, we'll get like 10 tool faces all at one time. That's not ideal. If we're just wanting to get the survey itself, then yeah, compressing the data and doing it that way works out for us, but it's extremely slow. But if it means the difference of finishing the well and not finishing the well, then they'll wait. The picture on the left is us, well, not us, but the rig, tearing the rig down. And the picture on the right is the same thing. They don't work 24/7 when they're actually taking the rig down. So the guys have a chance to rest. So that's when I go out and actually walk around and look at the stuff that they've torn apart. So they can tear this whole rig down probably within a day and a half and then start moving it to the other location. They're pretty efficient. Oh no, you did that, didn't you, Soph? Good one, Sophia. And that's my Radio Shack. So, yes.
How much do you
International work?
We have had some offers to go down to South America, but our company is quite small. We're based out of Grand Junction, so most of our stuff's in the Rocky Mountains. Yes.
You're talking about frequencies that you're measuring between 1 and 9 hertz.
Mm-hmm.
You have a dipole antenna in the ground. Where are the radio frequencies?
Would
Is a 9 hertz signal radiating radio energy?
Yeah, yep, it is. So then,
Is that primarily passing back up the drill string or out through the ground?
so we can do it 2 different ways. Usually we'll set up this system where we can see, we can switch between, depending on which is better. If we want to listen to it up through the drill string and the signal is strong enough, we'll do it that way. If not, we'll rely on the antennas that are out into the, behind the rig.
How big are those antennas?
They're just copper rods that we pound in the ground. So it's pretty basic. And then we just have a cable that hooks onto the back of the downlink box and goes. So this actually takes the signal from here and then goes into the back of here.
Are you using fiber optics or is it just raw copper cable?
Just copper cable. At those frequencies, we don't really need to, we don't have to really worry about loss. I was going to show you just some of our electronics. I'll pass it around. This is the actual, the brains of the system. So this is actually the same as this, and I just took the potting out of it so you guys can see some of the components. So I'll pass that around. So this is what has the accelerometers, the magnetometers, essentially everything goes through here. Oh, actually, let me see that.
When all those pieces are put together, they're gonna bend as they go through the
Yep, they bend as well. Yep, the whole system is made to bend. It seems weird. So this guy is so that's the brains of the system, and then this guy will slide inside of here, in the side of this. And the data goes from there, sent up to the dipole, makes its calculations, and then we'll send it up through the top of the dipole. And this is our gamma module. And it just is essentially just a receiver. And I'll just leave the batteries up here for you guys so we don't have to pass them around. Yeah, that's it. Any questions?
Thank you.
You're welcome. So you guys are free to come up and look at the stuff. Just don't drop it. No, it's all right. They're all parts that are out of commission anyway. Thank you.
So does your company insure those? What happens when you lose a tool? That's gotta be a lot.
Yeah, so the client can opt in or out of the insurance. Most of the time they opt out of it. So a string like that'll be, oh.
They're desktops, they're Dell desktops.
Give it to him?
No, we're just gonna do
Oh.
Yeah, well, we usually give them to recycling, but none of the recycling companies around here wanna touch it. They don't even wanna do it anymore, so it's not cost effective, I don't think, basically.
So does anybody else have any, show and tell things, experiences or anything? The state GOI or just on if you wanna work some DX. They're on for 30 days. It's, kinda controversial and, Mike isn't here to explain everything, but what it is a box they're dropping on, you can't get permission to go on